did you have any questions? Yes.
In the chapter for the homework problems, there was one, or there were two questions where it was like assign formal charges to the atoms and the molecule, and then but it was like an A, B, C, and it like gave you like -2, 1, 0, whatever, but it didn't tell you which atom it was for.
Okay. So let's
I
see.
have the number. It was like 1.8 and 1.
All right. Let me see if I can bring up the top hat book here.
Is there any way to see the answers for the homework?
Good question.
Because I was doing these, I'm like, I don't know if I'm getting these right.
Oh.
Yeah, if you look in the grade book, it says that it won't release.
Oh, okay. There's probably a button I have to push.
Okay.
Which I probably will push at the end of the day.
Okay.
We've made homework easier.
Also, is there a way that, for some reason, it just takes forever to load the book and do anything on it? Is there like a suggested browser, or?
I use Chrome for pretty much everything. I don't know. I'm not quite certain. It might have to do with, and let's see, you guys are all probably logged. If you're logged on here, it's with the guest.
It happens at like my house too, though.
Okay.
I think it's just like a lot to process.
Yeah, because I realize it's like one big
Like the
file.
drag and drop questions. Those are
You're like
so
20 minutes. No, those are so hard because you don't move up.
yeah.
Try
Oh.
to get the mobile app. It works a lot better.
Like on your phone.
Yeah.
Yeah, there is a mobile app for there is the mobile app for both, I think, an Android as well as a Apple. Okay. Since I don't answer the questions, I'm not quite sure. What was question 1.8? 1.8. Okay. It's even a little bit slow on mine too. Come on. I went too far. Okay, 1.8. We're getting closer. 1.9, 1.8. Okay. So 1.8, assign the formal charges to the atoms in the Lewis structure below. So just, I said this yesterday, but I just want to make sure. So for chapter 1 and maybe for chapter 2, well, ideally what I'd like you to do is for the reading assignment for the class period, if you could go through that in the textbook and then answer the questions that are in that reading before you come to class. We're going to get to a point where I'm going to expect that, but it may not be during the first couple days of class here because we're trying to get caught up from yesterday when you didn't have access to the textbook, and some of you still don't have access to that textbook. So by the end of the week, I would like you, by the end of the week, meaning Friday, to have all the problems in the chapter for chapter 1. And that may be the case for chapter 2 as well, since we're going to start that tomorrow. But normally, I would ask you to do those problems as you do the reading for that day, and then we can start with the questions like this. So for question 1.8, assign the formal charges to the atoms in the Lewis structure below. And so, let's see. Do you have a show? You don't have a show correct answer button, do you? Okay. I think I have to click something, which I will do after. I may do it in the break. Okay, so what am I looking at here? To the atoms in the Lewis dot structure below. So what am I not seeing here? I'm not. Yeah, that's my question too. My question is, where's the C and the O and the... So let's see, if I said,
I just assumed it had chemical knowledge, like,
good question. So, you know what, let's skip right to the correct answer. Well, let me ask you this. Hydrogen's always going to be 0, right? What about this carbon? What's the formal charge on that carbon?
0.
0? We all agree it's 0? Oxygen?
0.
0?
No, it's 0.
Is it 0 or -2?
0.
It's formal charge. It's formal charge. Its oxidation number is actually -2, but it's going to be a while before we get to the oxidation number. So its formal charge is 0. How do we get that? So we say, okay, the oxygen has 6 electrons in the neutral atom. It owns all the lone pairs outright, so that's 4. It owns 1 in each one of these 2 bonds. So it has 6, it came with 6, it has 6, 0 because there's no net change. Oxidation number wasn't in this chapter, was it? Well, if you did the oxidation number of organic molecules before, that's -2. Right, so it would be 0. So my guess is that since they're all 0, it would have to be 0. So let's just see if the correct answer is 0. But that's not intuitively obvious. That's why this is that's why I grade these on participation, that you answer the question as opposed to getting it correct. So that would have kind of thrown me as well. And then I think I have to click for it to give you the hint in the explanation.
Good.
But let's say okay, what about the NO? What about the nitric acid? And I added the question below that, I guess. So what about the NO? They're both 0 as well? Okay. What's wrong with it?
It wasn't wrong. It was just like, what's unusual?
I think it said, yeah, I think that was actually, that's a question that I added.
Oh.
The second one, what's unusual about the Lewis dot structure for nitric acid?
It's just that it has like 1 electron.
It has an unpaired electron. So that's what's unusual about it, was that it had an unpaired electron.
so like in reality, it would be open for the hydrogen to come by or something like that.
Well, that's the issue with nitric oxide. So there's a lot of drugs that have been developed that generate nitric oxide when they're in the body. And the reason they're generating nitric oxide is because with that unpaired electron, it wants to react with something to fulfill its octet. And so it's a very potent drug when it gets into the body, because it will immediately react in order to get that nitrogen its octet. It won't necessarily grab an electron from something as much as it'll react with something to then immediately form that bond. So it kind of is a it opens up your blood vessels. It's like a vasodilator. So there's a lot of drugs that are based on delivering nitric oxide in the body, and that's the reason, because it's so reactive. So I asked that question, and quite honestly, I'm not quite sure if it'll grade it itself. Did you have any other questions about? Yes.
I had one from the lecture yesterday.
Okay.
You're saying that the pi bonds are easier to break, and that but they're also double and triple bonds. I was kind of confused because I thought double and triple bonds were hard.
Okay, so let me clarify my terminology there. So let me play. So in terms of breaking bonds, when we have let's say a carbon, when we have like a carbon-oxygen double bond, we'll take that same molecule that was in the homework problem. Overall, if I want to break that CO double bond, I'm going to have to provide energy to break the pi bond, and I'm going to have to provide energy to break the sigma bond as well. And so there's two different energies that I have to add to break both of those bonds apart. So overall, it's harder to break a double bond than it is a single bond, and overall it's harder to break a triple bond than it is a double or a single bond because I'm breaking both of those bonds. However, because the orbital picture of that we've got this sigma bond that's holding the atoms together, and then we've got the sideways pi bond. I can break the pi bond and the molecule will stay together. So of those two energies, the pi bond is less than the sigma bond.
Is it just like in this?
In usually all the cases, it's easier to break the pi bond. The number for the pi bond is lower than the number for the sigma bond. But you add them up, and since it's a pi bond and a sigma bond, it's harder to break a multiple bond overall, to break it completely apart, than it would be to break just a sigma bond. Because we're going to break pi bonds all the time when we do reactions. So overall, it's harder, but the sigma bond is easier to break, the pi bond is easier to break than the sigma bond. And you can break the pi bond and the molecule will stay together. When you break the sigma bond, then the atoms are going to fly apart. So that's what I meant by that, if that wasn't quite clear. What other questions do you have? And this is why we start this way. So,
Question about the homework. I was having issues with some of like the hybridization questions.
okay.
I don't know where exactly. I mean, it was in hybridization.
Let's do this. Let's go back through hybridization as we sketch out the orbitals,
Okay.
and then maybe that'll be clearer when we do that.
Yeah, that's fine. I just needed the clarification.
Yeah, because what I left off in the last 5 and then extra 10 minutes of class yesterday was where we want to start. So let's say, for instance, let's just start with this molecule, this HC double bond O. This molecule is called formaldehyde. So that's the thing you put dead things in biology, the preservative. There's a big issue, bless you, that formaldehyde is it's in a lot of products and it degasses and it's a little carcinogenic, so it's an industrial byproduct. But if we look at formaldehyde, let's say I wanted to sketch the orbital picture, which I started to do as I was answering that first question. So the first thing we need to do, if I asked you that kind of question of sketch the orbital picture of this molecule, is we need to know what the hybridization of each atom is, each non-hydrogen atom. So we need to know what the hybridization of that oxygen is, and we need to know what the hybridization of that carbon is. Now, there's many ways we can do that, but let's start with the idea of Vesper geometry. So when you have the VSEPR geometry, what is the correlation of that to hybridization? So if we have a linear Vesper geometry, that corresponds to what kind of hybridization? Well, it's going to correspond to SP. Okay. And the way we can think about that is, remember, for the SP hybridization, we had two hybrid orbitals. Here's the critical part. The hybrid orbitals generate the geometry, not the p orbitals. Only the hybrid orbitals generate the geometry. So when you have two hybrid orbitals, again, big balloons, they're going to be as far away from each other as possible. So linear is SP, and then trigonal planar is going to be an SP2, because now we have three, and I'll sketch out the pictures of this in a moment. If we have tetrahedral, the tetrahedral is going to be SP3, and then we can just continue on. The trigonal bipyramidal, well, I don't know what that is yet. Let me develop that. So let's stop at tetrahedral for the moment. So for SP, remember, an SP hybridized atom is one that has the two SP hybrid orbitals 180 degrees, and it's going to have two unhybridized P's. So what I always do is I always shade in the hybrid orbitals, and then I leave the P's unshaded. So there would be an example of an SP hybridized atom, any atom. Doesn't matter what it is. Because what I want to do is I want to work past carbon. And I'm going to have to if I have the oxygen. For SP2, what's an SP2 hybridized atom look like? It's going to have 1, 2, 3 hybrid orbitals, and then it's going to have the unhybridized P. And so those three SP2 hybrid orbitals are in the plane. So any SP2 hybrid orbital looks like that, or any SP2 hybridized atom looks like that. And then for SP3, the atom's going to have 4 hybrid orbitals, and so it's going to have its 4 SP3 hybrid orbitals with no P's. So that's the first step, is we need to assign the hybridization of each of the not hydrogen atoms. And maybe the way to start is to go back and assign the geometry first. Now remember, when you're assigning the geometry, we are taking into account the number of lone pairs and the number of bonding pairs around the atom, and a double bond counts as one bond, and a triple bond also counts as one bond. So we're ignoring the pi bonding. We're ignoring the different pi bonds. So if I looked at this carbon and oxygen in formaldehyde, what's the hybridization? Well, let me start with the geometry. What's the geometry of the carbon atom? What's the geometry of the carbon atom? What's the geometry of the oxygen? Okay, so take a minute.
You said the tree double and triple bond is
Yes, we're always treating double and triple bonds as one. And then for carbon, then we use A for linear, B for trigonal planar, and C for tetrahedral. So the question is, what is the geometry for that carbon? This is active learning. Right, that's so that way everybody's got some skin in the game. You might have to move your finger a little bit there. It's kind of technical. Okay, we have 7B's trigonal planar. So this is trigonal planar. How do we know that? I guess I forgot the first part of the formula, didn't I? Well, so for linear, trigonal planar, and tetrahedral, we need to have the number of bonding pairs. So around carbon, how many bonding pairs are there? There's 3. 1, 2, and then the double bond counts as 1. So around carbon, there's 3 bonding pairs, which is going to make it trigonal planar. Okay, 2 would be linear, 2 is linear, 3 is trigonal planar, and 4 is tetrahedral. Now, what about the oxygen? If we're going to assign the geometry of the oxygen, I have to add a couple more details. For these geometries, this number is going to be the number of bonding, sort of the number of bonding, the number of bonds, the number of single bonds, plus the number of lone pairs. So now I'm going to take my lone pairs and I'm going to throw those into the mix. Carbon doesn't normally have lone pairs. But if we want to do oxygen and nitrogen and sulfur, we're going to have lone pairs. So what do we do with them? What we have to do with them is we have to count them as if they were a bond. Why? Because the geometry of the atom is based on what? Well, here it's 2 lone pairs and bonding pairs. But I could also replace that by saying that it's linear because it has 2 hybrid orbitals. So what I'm really doing is I'm counting the number of hybrid orbitals around that atom. And the way I get to the number of hybrid orbitals is by determining how many sigma bonds there are plus the lone pairs, because the lone pairs always go into the hybrid orbitals. I might have said that yesterday. So really, this number of sigma bonds plus the number of lone pairs, it's really the number of hybrid orbitals as well. And if I know the number of hybrid orbitals, then I have S's and P's to add up to that. So if I've got 2 hybrid orbitals, sp. 3 orbitals, sp2. 4, sp3. 5, dsp3. We'll get to that. Okay, so this is all tied together. So if I look at that oxygen then, what would its geometry and hybridization be for the oxygen? Is it going to be A, linear, B, trigonal planar, or C, tetrahedral? So, what's that oxygen going to be, given that formula? So the question is for oxygen now, is it going to be linear in SP? Is it going to be trigonal planar in SP2? So A, B, or C? Is it going to be tetrahedral or SP2? Okay. All right, so we have 7 B's, which is SP2. Okay, so it's oxygen has 1 sigma bond and then 2 lone pairs, so that's going to have B3. Okay. So I can also simplify this by simply saying pi bonds don't count. And remember that in a multiple bond, the first bond is the sigma bond and the second bond is the pi bond. So 1 sigma, 2 lone pairs, 3 hybrid orbitals. That's going to make this also trigonal planar. And each one of these two then, the carbon and the oxygen are going to be sp2. Okay, so that's our first step. Identify the hybridizations of each of the non-hydrogen atoms. That's what we need to do. So we can use this chart. I'd strongly recommend rewriting that chart when we're all said and done because it's really messy right now. But really what we're doing is we're counting the number of hybrid orbitals by counting the number of sigma bonds and lone pairs. Because the hybrid orbitals can only contain, the lone pairs can only go into the hybrid orbitals, and the hybrid orbitals are the ones that are forming the sigma bonds that are generating the structure. So that's the first thing we need to do. So then for this molecule, let's go ahead and let's sketch it out. And I'm going to sketch that carbon-oxygen bond, or carbon-oxygen atom. Let's start with the central atom of carbon. What was its hybridization? sp2. So let's write an sp2 hybridized carbon. And again, the shaded orbitals are the sp2 hybrid orbitals, and the unshaded is the p. So there is an sp2 hybridized carbon. As a matter of fact, that's an sp2 hybridized anything, because I have not put electrons into it yet. So I could come over here to the oxygen, and I could basically do the same thing. And again, shade the orbitals so that there's sp2, 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 and then the unhybridized p orbital. So any atom that's sp2 hybridized is going to look like that. I haven't put the electrons in. Now the reason I oriented the two hybrid orbitals together is because that's how I'm going to form my sigma bond. Those are going to overlap head to head to form the sigma bond. Now we need to put the electrons into each of the atoms. So how many valence electrons does carbon have? 4, right? So each hybrid orbital gets an electron, and the unhybridized p gets an electron. 50% of its time it spends in the top lobe, 50% of its time in the bottom lobe. So that's like drawing a Lewis dot structure of carbon. Every orbital gets one electron. Now, how many valence electrons does oxygen have? It's got 6. So here we have to remember our rule that says the lone pairs can only go into hybrid orbitals, which means that only the unpaired electron can go into the p orbital. So I'm going to start out by putting the unpaired electron in the p. And then, where should the lone pairs, the 2 lone pairs, and then the other unpaired electron go? Well, remember the goal of this is to form the sigma bond. So the unpaired electron is going to go here. The lone pairs are going to go here. Why? Because I'm going to overlap the 2 sp2 hybrid orbitals, each having 1 electron to form the CO sigma bond. Because that's the ultimate goal. Basically what I have is this right now. So like I said yesterday, normally when we're writing our Lewis dot structure, that's what we would do, and then we would say, okay, let's pair up these 2 electrons to form the sigma bond. Now we're taking we're taking a depth above here and looking at how the bonding forms. What does that mean? That means I'm going to overlap those 2 sp2 hybrid orbitals to make the sigma bond. And in the book there were some problems that ask you to identify the specific orbitals that are overlapped in order to form the sigma bond. That might have been the question you asked about earlier. Now what about the hydrogens? The hydrogens are spherical 1s's, and so they should overlap with their 1 electron. They will overlap the 2 sp2s on the left-hand side. So in other words, it's like I'm doing this. And if I was doing the Lewis dot structure at this point, I look at the carbon, I look at the oxygen, do they have completed octets? No. So what do? I share these 2 electrons to now form the double bond. How am I going to form the double bond in the orbital picture? I'm now going to do a sideways overlap of those 2 p orbitals. The orbitals have to be parallel to each other when they sideways overlap, and now that's going to form the pi bond. And so with these 2 structures then, the Lewis dot structure and the orbital picture, I'm now describing how I'm forming formaldehyde and what orbitals are overlapping in order to form the sigma and the pi bonds. And also it tells me that the lone pairs are hanging outside the molecule in hybridized sp2 orbitals. So that's kind of the steps that we need to do in order to put the structure together.
The hydrogen or sigma?
The hydrogens can only sigma bond. So in other words, when you have a sphere, it can only go head to head. The only time you can get a pi bond is if 2 p orbitals each have an electron and they are parallel. So that makes sense? Well, we're going to do one. Or, sorry, you're going to do one here in a minute, or maybe more than one. But before I do that, I want to expand this literally into like expanded octets and where they come from. So I left off on the chart what trigonal bipyramidal and what octahedral were. And so let me just develop it the same way I did yesterday in terms of where you get those two. So let's do sulfur. So we know that sulfur has this Lewis dot structure. 2 pairs and 2 unpaired electrons. And if we looked at the electronic configuration of the sulfur, I'm putting in, it's 1s2, there's too many 2s orbitals. Actually, that's not going to work. If you have space above the 3p, you're okay. I need to start lower. Okay, so if you look at the electron configuration of sulfur, the 1 and the 2 shells, we could call them, are completely filled. So that's not the valence, those aren't the valence electrons we're going to use. We're going to use the 3s and the 3p. So if you're looking at the periodic table, you've got a 3s2, and then you've got a 3p. Right, so we would go 1, 2, 3, and then we pair up the first one. So there is the ground state electronic configuration for sulfur. And that electronic configuration would be great for something like H2S. So that's the sulfur analog of water. Right, we'd have 2 hydrogens attached to the sulfur with the 2 lone pairs. Perfect. That electronic configuration works perfect for that because the sulfur's got 2 pairs and 2 pairs of valence electrons and 2 unpaired. But there also exists a molecule called SF4. Well, let's see. Okay. So 1 electron, I'm going to bond those 2, and then I've got 2 more pairs, so there's my SF2. And so in order to form SF4, I'm going to go F and F. So there's my SF4. So SF4 has 3 sigma bonds and a lone pair. That's an expanded octet. Is sulfur allowed to do that? Yes, because it's row 3 and lower, but the question is, why is it only row 3 or lower? Okay. And so that's the question we want to address here, as to what, and what does that look like? What does SF4 look like? Right, so I'm back to yesterday. Remember, we started with a carbon that only had 2 unpaired electrons and could only form 2 bonds. And so what did we do? We said, well, let's take one of those electrons, let's go to the excited state, and let's move that electron up. Okay, so what's above 3p on the periodic table? No laser pointer, no stick. Over 90. gonna make, what's this? 1, 2, 3, 4s, and then the sulfur on the other side is 4p's. So what's directly above the 3s for 3p? 4s. So here's what I'll do. I'll kick one of the 3p, I'll kick this electron from the 3p up to the 4s. Now notice I didn't do that. So if I go into an excited state and I move that 3p, I move one of these 3p electrons up to the 4s, I'm going to get 4 unpaired electrons to form my SF4. But here's the problem. The quantum mechanical rules say that if you're going to mix orbitals, if you're going to hybridize them, you can only hybridize orbitals with the same principal quantum number. And 1, 2, 3, and 4, the shell number, is called the principal quantum number. So I cannot mix a 4s with 3p's and 3s's. That's not allowed. So for sulfur, is there something with a 3 in front of it? There is, right? Because if I come over here, which I might be able to reach, this is 4s, what's that? That's the 3 Ds. Now, are they higher in energy? Yes. There are 5 of those. But if I pay a little bit of energy cost here to kick this electron up to the 3D, I'm going to get it back and more when I hybridize. Because when I hybridize, one of the things I forgot to say yesterday is that, remember, we had the sphere plus the p orbital, the s plus the p, made an sp3 hybrid orbital. There I had to pay a cost too in going to the excited state, but I got that back. And how did I get that back? Well, when you're trying to bond a p orbital or an s orbital, the electron density is all over the place. Like with a sphere, the electron density is everywhere. I'm going to form a stronger bond if I can concentrate that electron density into a smaller volume. Here, 50-50. But the reason there's a big lobe and a little lobe is because the big lobe now has a concentrated electron density. So when that sp3 orbital, or sp2, or sp, that larger lobe then overlaps, you're going to get a stronger bond. So, I mean, energy is to chemistry reactions as money is to politics. If you want to understand why chemistry reactions occur, you've got to dig into the energies. It's true for politics and money. Money and power. That's another class. So I have to pay a price to get it into the excited state, but then I'm going to get that back by forming a stronger bond, because now that energy, or the electron density, is going to be concentrated. The same thing's going to be true here. If I can have a little additional cost, then I can hybridize everything. So what I'm now going to do is, I'm now going to take my 3D with its 1 electron. I'm going to take my 3p that now has 3 unpaired electrons, and I'm going to take my 3s with the pair of electrons. I'm now going to mix those all together. And I mix orbitals, not electrons. So I'm going to mix the d, the p, and the s, and so I'm going to get 5 orbitals, and it's going to be each one of those is going to be d sp3. Or sp3d, I don't care. But I'm going to get a dsp3. I'm going to get 5 orbitals now. Okay. What's the geometry for 5 orbitals? Because quantum mechanically, we can only hybridize orbitals that have the same number in front of them. So I can't mix a 4s with a 3. I can't mix any 4 with a 3. I can only mix 3s with other 3s. Those are the quantum mechanical rules. So that's why I have to skip it, because if I do that, then I can mix all those orbitals together. And in the end, I'm going to get stronger bonds, so I'm going to pay that price. And honestly, the 3D is not that much higher in energy than the 4s. So it's not like I'm paying a tremendous price here. But that's the rules. In carbon, the issue is, and I'm getting ahead of myself. So I can only mix the 3s. So then I get 5 dsp3s. Because I'm mixing 1, 2, 3, 4, 5 orbitals together. So I'm mixing the D, the 3 Ps, and the S. Because sp3 was 4. So we're right. What's the geometry for dsp3? What's the geometry of having 5 clouds around an atom? Trigonal, bipyramidal. You can't talk about VSEPR theory really without hybridization. So I've got 5 clouds of electron density around that sulfur. And so remember, that's going to be trigonal bipyramidal. All 5 of these orbitals are now going to be hybrid, and they're going to take on the trigonal bipyramidal geometry. So that's the trigonal bipyramidal is basically a combination of the trigonal planar and the linear. Is sulfur allowed to do this? Yes, because it can form an expanded octet. But now, so it can form an expanded octet because it's row 3 or lower. Why can elements only form expanded octets if they're row 3 or lower? In other words, why can't carbon? Why can't nitrogen? Why can't oxygen? It wouldn't have to be the 3D, it would have to be because they're row 2. So if I wanted to do this for carbon, I'd have to expand it to a 2D. And there is no 2D. Wow. I actually think in certain quantum mechanics, they actually invent a 2D, but it's not real. And if you think about the carbon, if we did that, we'd have to mix the 2s and the 1s because we'd have to take the electron out of the 1s. So it's just not possible. But there is no 2D orbital. The first place we have a d orbital to be able to form a dsp3 hybrid orbital is row 3. That's the first time we have a d orbital. So that's why that rule is row 3 or lower.
So the other 10 electrons are in 2p, 2s, and 1s, but they're just not hybridized.
Right, because they're the core electrons. We only form bonds from the valence electrons. And remember, the valence electrons are always the ones that are the outermost. They're the ones with the biggest principal quantum number. So those are all, so these ones, not those ones. Those ones are the core electrons, and then these are the valence electrons. And it's always the valence electrons we form bonds with. Now, had you heard that explanation in your general chemistry class? It's probably a long time ago to remember. So sometimes people just skip right over this. In the years that when I teach general chemistry, I always go over it because I know I'm going to end up talking about it in the first couple weeks of organic, or the first couple days. So that's the reason why we have these expanded octets. And can I do this again? Because I still have a pair in the 3s. So could I promote the electron from the 3s up to the 3d? Yes, I can do that, and I'll do that in a moment, because now I'll end up with a D2 sp3, which will give me 6 hybrid orbitals, and 6 hybrid orbitals is going to have what geometry? Octahedral, and so that's where the octahedral comes from. So for the most part, we're only going to deal with linear, trigonal planar, and tetrahedral, but we will actually at some point invoke the trigonal bipyramidal.
On the homework, it sometimes doesn't get anyone who say you are going to suffer, but its answers should be just like,
Well, you can answer. Let me come back and talk about that. The bent, the T-shape, the seesaw, all of those. The book's probably asking for that, and they have a chart, I think, that has those geometries. I only deal with electron paired geometry, so when we're talking about different geometries, when I said that when I say that this sulfur, so let's put the electrons in the sulfur and then let me. Okay, so here's my structure. So what did the sulfur have? The sulfur has 4 unpaired and 1 pair. So we should probably go 1, 2, 3, 4, and then the lone pair will go there. Now, you could say, how do you know to put the lone pair in one of the 3 planar, trigonal planar, and not in the linear? Because I think I remember that's where it goes. If you put it in the other one, it'll always be fine. But we're trying to minimize the repulsions, and so in that case, I think there's just a couple of repulsions as opposed to 3. So this would be the electronic, that would be the orbital picture for the sulfur, with every one of these being dsp3 hybrid orbitals. And then the fluorines would come in and add to those. Well, it would add 4 of them. And then with the lone pairs, that would be those. Okay, bend, T-shape, etc. So when we write the geometry that looks like this, with the lone pair, I consider that sulfur to be trigonal bipyramidal, because I take into account the lone pairs. Because my interest in organic chemistry is to take that electron pair geometry and move it to a hybridization. And if I ignore the lone pairs, I can't. So when you're talking about a molecular geometry, you're doing just that. I can't see the lone pair of electron, all I can see is the bonds. So when I look at that molecule, I don't see 5, I just see 4. And so then this would be the T-shape or the seesaw. For water, it's bent, because I can't see the other 2 lone pairs. So those are molecular geometries. The book is probably asking you for molecular geometries as well, but there's a table for you to be able to do that. So in water, I would say the oxygen is tetrahedral, but water itself overall is bent, because it's got a molecular geometry. NH3 would be pyramidal, because I can't see the top lone pair. So I guess even refining that a little bit further, when I talk about the electron pair geometry, I'm specifically talking about the atom. When we're talking about a molecular geometry, we're looking at the overall molecule. So it's going to ask you for both. But it's also going to tell you, is the T-shaped or the seesaw more stable? And I forget off the top of my head. I think it's the one where the lone pair is in 1 and 3. So yeah, you can go ahead and do those. In reality, if I gave you those on a test, I'd accept either one. So that means for the sulfur, if I wanted to form SF6, the SF6 is going to have a sulfur now with 6 unpaired electrons, because each one of those is going to be used to bond the fluorine. And so now I'm going to end up with the octahedral geometry. And where did that octahedral geometry come from? It now came from promoting the lone pair, one of the lone pair electrons in the 3s up to a second 3d, so that now I can go into an even higher excited state for sulfur. And so now I've got my S with my 3p's and 2d's, so this is now a D2 sp3, which is now 6 hybrid orbitals. And those 6 hybrid orbitals means that the sulfur is now going to be 1, 2, 3, 4, 5, 6. And so now those are all D2 sp3 hybrid orbitals. Phosphorus only has one less electron, so phosphorus, the max it can do is D sp3. It can't do D3. Sulfur can do D2 sp3. It's got an extra electron. So sulfur can do sp3, dsp3, and D2 sp3. If I was to look at the phosphorus is 3s 3p3, so it's 3s and then 3p3, and so then if I look at the 3d, the best I can do for phosphorus is to move this electron up here. So the best you can do for phosphorus is a dsp3. There's no D2 sp3 because it doesn't have that extra electron to sulfur. Those are the 2 big ones that we use in expanded octets. So then drawing the structure of this would be relatively easy because there's no p orbitals to worry about for the sulfur or dsp3 or D2 sp3. There's no need to worry about pi bonding because there's no p orbitals. And so those would be for fluorine. Fluorine is tetrahedral, and so fluorine would overlap its 1 unpaired electron with the sulfur to form the sigma bond. And so if I put 5 more fluorines around there, that would be SF6. So that's where the expanded octet comes from. That's how we can draw an orbital picture of the molecules. But in order to do that, what do? We have to figure out what the geometry is around that atom, correlate that to hybridization. Every sp2 atom looks exactly the same. Its difference is when you start putting the electrons in. Which takes me back to one thing that I need to stress is that when we form an sp2 or sp3 or D2 sp3, I'm only mixing the empty orbitals and then I'm putting the electrons in. I'm not mixing the electrons. So it's kind of like when you, in general chem, when you did 1s1, 1s2, 1, the 1s, 2s, 2p, 3s, 3p, 4s, that structure already exists. You're just putting electrons into it. When you hybridize orbitals, that structure now exists. I'm putting my electrons into that structure. That's why I could use X to show the hybridization, because it doesn't matter what the atom is. Okay. And so this is really of general chemistry stuff. This is really the first that is related to organic. Because how these orbitals are formed gives me the structure, gives me the shape, and so that's where we kind of pick it up from there. But to get here, what did I have to do? Valid Lewis dot structure, if there were resonance structures, and then turn it into a Vesper geometry and turn it into hybridization. So again, that's probably 2 months of general chemistry in a day and a half. Okay, does that make sense? All right, let's take a 5-minute break. And then what I'm going to do is I'm going to talk about polarity, and then I'll come back at the end, and we'll do some problems. We'll do some problems on polarity, and we'll do some problems on doing this orbital picture, and then we can do that. And we can work together once I break you up. I'm going to put you into groups, and they're going to always change because I have a randomizing thing to be able to do that. There's still 2 people that aren't here
Stephanie's not.
at all. Ever? Okay. I hope she got her money back. $11 people. I know there's one who's going to come next week. Quarters. I didn't know schools were still on quarters, but they are. So, okay, then. Okay, so let's talk a little bit about polarity, because that would be the end. So once we can draw the Lewis dot structure, once we can convert it to a geometry, the next thing we need to know is that molecule polar or non-polar. So when we look at the idea here of polarity, and this is going to be the last, these slides are the last group, starting on page, well, it doesn't matter because they started over again. So it's the last group in the notes that I handed out yesterday. So in order to determine whether a molecule is polar or not, we first of all need to remember what polarity is. And the polarity is basically deals with electronegatiivity. So if atoms have different electronegativities, then they're going to create a polar bond. Now, let's just talk about the different kinds of bonds that you can get. First of all, you could get an ionic bond. When are you going to get an ionic bond? When you take something on the periodic table, when you take something from the left-hand side and the right-hand side of the periodic table, and you bring them together, that's when you're going to get ionic bonding, because the electronegativities are so different between those elements that one's going to give up the electron to the other. So for instance, if I look at sodium and chlorine, sodium, an electropositive element, chlorine, an electronegative element. When I bring those together, what happens, the sodium gives up its electron to the chlorine. I form a sodium ion and a chloride ion, and so I get ionic bonding. So I only get ionic bonding when I have ions. And so that's when we get ionic bonding. Bring something from the left, bring something from the right. How about this? Anytime you got a metal, you're going to have ionic bonding for now. When do you get a covalent bond? Well, what does covalent mean? Not complete transfer, but sharing. And covalent would be completely equal sharing. When are you going to get completely equal sharing? Well, I'm gonna say you get completely equal sharing between two atoms if they're exactly the same element. So a diatomic molecule, a carbon-carbon bond. So we're gonna make this extreme. We're just gonna say, you know what? You get equal sharing when the atoms are the same element. Now, the idea of an ionic bond to an unequal sharing, this is a continuum. It's not, there's no set defined, breaks, so it's a continuum, but we're just going to make it, if it's the same element, it's equal sharing. And then we can have a polar covalent bond, and a polar covalent bond is going to involve unequal sharing. I mean, it's sharing, but it's unequal. So you can apply that to whatever situation you want. Maybe a car is unequally shared. So if you have this unequal sharing, and when's that going to happen? That's going to happen when you have non-metals that are bonded. And so where do we find the non-metals? We're going to find the nonmetals on the periodic table, basically from boron diagonally down here to iodine. So on this periodic table, which is going to disappear today, the green elements in that box, and hydrogen. So in other words, if I bond a carbon to a nitrogen, that's going to be a polar covalent bond. If I bond an oxygen to a hydrogen, that's going to be a polar covalent bond. Now, what about a carbon and a hydrogen bond? We're going to see that tomorrow. And so when you have a carbon-hydrogen bond, that's going to be what I call it, a relatively covalent. So I'm going to treat a carbon-hydrogen bond 9 times out of 10 as if it was a covalent bond, a pure covalent bond. And 1 time out of 10, I'm going to actually invoke their electronegativities. So we're going to deal with covalent and polar covalent bonds when we're talking about electronegativity and when we're talking about polarity. So we're not going to deal with ionic because we'll make ions in organic, but not very many. So that's going to be most of our situations. So when we look at a bond, if they're not identical atoms, we're going to look on the periodic table and we're going to say, okay, X is bonded to Y. If X is more electronegative, it's going to be delta minus. If Y is less than electronegative, it's going to be delta plus. So in other words, I'm going to use my same delta pluses and minuses as yesterday to indicate which atom is unequally shared, the electron. So where the electrons spend most of their time around one atom, that's going to be slightly negative, and it's going to be slightly positive around the other one. Perfect example of that is if I had an OH bond, the oxygen would be slightly negative and the hydrogen would be slightly positive. So that's where electronegativity comes into this. What's the dipole moment? These are my Gen Chem slides. So they have all the mathematical formulas in it. As I told somebody or as I told a presentation last week at the conference I was at, I'm like, I was in analytical chemistry or in a session with analytical chemistry. I'm like, I'm an organic chemist, so numbers, we'll only go so far with the numbers. Right? We usually try and simplify things as much as possible. But basically, a dipole moment or a bond dipole moment is how we measure how polar covalent that bond is. And it depends on two things, which we don't need the math for. The difference in the charge, the difference in the electronegativities, which is going to give us the difference in delta plus and delta minus, and then also how far away those delta plus and minus charges are from each other. The farther they get away, the less the polar the bond, the closer they are, the more polar the bond. So the polarity of the bond is like electrostatic attraction. When I'm teaching general chemistry, I'll usually make this statement. I'll usually say, well, what if aliens, if there are such things, and that's for another class, what if they came down and they said, hey, we want to know about chemistry, but we only want to know what is the most important concept that you could learn in chemistry? And I would tell the aliens, I would say it's electrostatic attraction. Because that's how we're going to explain how atoms are attracted to each other, by the positive negative charge. More positive and negative, the stronger the attraction. The more delta positive, the more delta negative, the stronger the attraction. That's how we can talk about acid-base chemistry. So to me, that's the most important thing. And so when we look at polar bonds, that's what we're looking at, is the difference in the charges and how far away the charges are from each other. Fortunately, in organic, it's either polar or it's not. So we don't have to worry about we might have to worry about the strength of that, but that's going to come from, again, electronegativity. And then molecules are polar because if you put them in between two plates that are oppositely charged, they align themselves with the delta positive end towards the negative plate and delta negative end towards the positive plate. That's how we know a molecule's polar. If we don't get any alignment, it's not polar. Which gets us to molecular moments or molecular dipoles. So how do we determine a molecular dipole? How do we determine if a molecule is polar or not? Well, if a molecule is polar, it has to have both of these conditions. It has to contain a polar covalent bond. So how did we define a polar covalent bond? Two elements that are different. Because then there's some level of polarity there. But not a CH bond. CH bonds are not going to give us a polar covalent bond. It'll give us a relatively non-polar covalent bond. But it also have to have a non-zero molecular dipole moment. What was that? What that is, take the molecule, and a couple ways we can do this if we have water. What we know is that for water, the hydrogens are delta positive, the oxygens are delta negative. We can use arrows to indicate that. Sometimes when I write my arrows, I'll put the little plus here to indicate that that's where the positive sign is for arrows, and we're going to do a lot of arrows here for the remaining number of weeks. Arrows always, the head of the arrow is always where the negative is moving. So the head is the delta minus end, and the tail is the delta plus end. And what we do with those individual bond dipoles is we add them up sort of in a vector, sort of like vector geometry. So if we wanted to, we could start at the atom, central atom, and then we go up with the blue one in exactly the same direction and same length. The length is the difference in the charges. And then when we take the next one and we go tail to head, red tail to head, and then we go from the beginning to the end, and that tells us where the dipole moment is. The reality is we can simplify this pretty easily. So that's how we would determine the dipole moment. What is a dipole moment even? What does it mean? Here's what it means for water. It means that, if you remember the water had the one arrow this way and the other arrow that way. The end of this arrow is going to be where the delta minus is, and the beginning is probably where the delta plus is. So for water, what it means is water is polar. Why? A molecule is polar when its charge on its surface is uneven. So for water, and you'll see these pictures in the book, you see these pictures everywhere because they're so easy to generate. The red means delta minus, and the blue means delta plus. So in water, near the oxygen is delta minus, and near the hydrogens is delta positive. And so water is a polar molecule. Yesterday we talked about water being, I drew it linearly. I didn't tell you that's normally a question I use to trap freshman general chem students, because they'll say, water's linear. Well, wait, is water polar? It can't be linear if it's polar. So that tells us that whenever these geometries I'm working with, they are the Vesper geometries, the shapes. Not the Lewis dot structure. We can't get polarity from a Lewis dot structure until we make it three-dimensional. Another example is ammonia. Ammonia with the nitrogen is more electronegative than hydrogen. And so nitrogen's delta minus then, the hydrogens are delta plus. So in the overall molecule, around the nitrogen is delta minus, around the hydrogens is delta plus. They do not have the same charge around the molecule. That's what makes it polar. So you have to have an unequal charge around the molecule for it to be polar. Now, notice there's one word I never used here. What also happens to be where that red color is in ammonia or in water, the lone pairs. Notice I never said anything about electrons, because it's weird, but in polarity, the lone pairs aren't discussed. There's no arrow for the lone pairs. It's because what it is it's a difference in charge. And so the lone pairs aren't talked about, although they might be in a minute. Bless you, but they're not discussed. So yeah, usually where the lone pairs are is going to be negative. But not because of the lone pairs, but because of the difference in charge. Oxygen and nitrogen being more electronegative than hydrogen. So it's got the extra delta minus. And so we could skip ahead here to do CH2F2. Now CH2F2 is tetrahedral. So here is CH2F2. The CH2F2, how would we get the geometry? Well, we'd have to do this with a tetrahedron in 3 dimensions. So the carbon-fluorine bonds here would be in this direction. Then the carbon-hydrogen bonds would be, let's see, the carbon-hydrogen bonds would be in this direction. And you might say, well, those cancel out. And so here's where the geometry might break down, so we'll make it fairly simple. when you have a tetrahedron, or trigonal planar, or linear, or trigonal bipyramidal, or octahedral, I think that's it, right? So whenever you have a geometry, if you have the same atoms at all the positions, it's non-polar because they cancel each other out. If you do not have the same atoms at all the positions, they don't cancel each other out, and so it'll be polar. So we can break that down and not even go through the geometries by just saying that. So in this case, with 2 fluorines and 2 hydrogens, they don't have all 4 atoms being the same. On the other hand, if I had methane, methane is tetrahedral, has all 4 hydrogens the same atoms. Methane is not polar, because all those carbon-hydrogen bonds will cancel each other out. Yeah. Oh, you are exactly right. Why did I do that? They all point in the same direction now. So they all point like this. Yeah. That happens. Me making typos happens. Sometimes a lot. Someday I'm just going to teach the class completely wrong and see how many people catch up and see how many people stop. So I will do that, so feel free to feel free if something doesn't make sense to tell me, because 9 times out of 10 it's a mistake on my part. Oftentimes I'll say, I'm trying to show you what kind of mistake you could make in the future, but it's really a mistake. So what does that also mean? And I guess I don't have the picture of this, but I can show you this in a moment. Carbon tetrachloride. Carbon tetrachloride's used in dry cleaning. It's pretty bad. Anything with a chlorine in it, like if we use dichloromethane in lab, which is CH2, which is CH2Cl2, that's not the best solvent to use. It's not very environmentally friendly. We'll still use it. Maybe you'll use it over the summer, but then that's it. I'm eliminating it. But it's basically a polar solvent. So is carbon tetrachloride polar or non-polar by the rules I just gave you? Non-polar? We agree it's non-polar? Because all the atoms are the same, so they should cancel each other out. So here's a big picture of carbon tetrachloride. Okay. There is the picture of it with its charges. And they're green. Green is like negative. But notice the shade of green in the molecule. Is there any variation? It's all the same color green, right? What does that mean? That means that around the molecule, it has the same negative charge everywhere. Is that non-polar? Yes, because polar molecules have different delta plus and delta minuses around it. If it's all the same delta minus, it's not polar. So that's why carbon tetrachloride, is nonpolar, because there's no difference in the delta minus charge around the surface. And so if it's nonpolar, that means it dissolves nonpolar things like greases and oils, which makes it perfect for dry cleaning. So that's also a definition of polarity and nonpolarity. Is this is polar because it's got delta plus and delta minus on the surface. CCl4, not, because there's no difference in the charges. So is it possible to be totally negative? Yes. If there's no variation, it's nonpolar. Yes. And also because if in this structure all the polar covalent bonds here, all the dipoles, are going to cancel each other out. Because in any geometry, if you have the same atoms, they're all going to cancel each other out. So that's how we can easily tell if something's polar or nonpolar, just by simply looking at the geometry. And if they all are the same, it's nonpolar. If that's not the situation, it's going to be polar. So more times it's going to be polar than nonpolar. Now, this CH2, if this was CH2Cl2, how polar would it be? Would it dissolve in water? Well, that's a whole other issue. We consider it to be a polar molecule, but is it polar enough to dissolve in water? And the answer is no. Not a lot of it. So how do we determine if a molecule is polar or not? We simply look at the Lewis-Dot structure, the Vesper geometry, the 3 dimensions, and then we look at the bonds. So let's do one. It's a good one. CO2. Is CO2 polar or nonpolar? So I'll give you a minute or two. Is CO2 polar or nonpolar? So what do you have to do? First step is draw its Lewis-Dot structure. And how is this bonded? Oxygen, carbon, oxygen. As I said yesterday, I always have to do the skeleton. Which may want to do is yes. To do it. Okay, so CO2, we're able to draw the structure. So for CO2, what's its Lewis-Dot structure going to look like? What's the geometry around the carbon? See what you said. You said it. Yeah. Linear. You know, don't be shy. If you're going to give an answer, be aggressive with it. Even if you're aggressively wrong. No, you were right. So it's linear, which means it's set up like this. So there would be by dipole moments. Do they cancel? Yes. SO2. Is SO2 polar or non-polar? And again, same skeleton. Sulfur, oxygen, oxygen. So is SO2 going to be polar or non-polar? Well, CO2 is non-polar. It's non-polar. Because it's linear and it cancels each other out. So what's SO2? Well, so we would go sulfur down. What we have to do is we have to stick in we got 3S, we got 3S2 and 3P4. And the question is, how do we form the bonds from that? So, how do we know if sulfur is expanded or not? Well, let's do this. How many electrons around sulfur? Valence electrons. 6. 1, 2, 3, 4, 5, 6. How many around oxygen? Okay, let's form our bonds. Sigma bond, sigma bond. Is everybody happy? No, sulfur is, but not oxygen. So what am I going to do? My pi bonds. So in the end, my sulfur is going to look like this, right? Because I use 2 of the lone pairs, 2 electrons in the lone pairs of the 4. So sulfur is going to be a little bit different than SO2 is going to be a little bit different than CO2 because sulfur's got that lone pair. So that's the next question. So if I asked you right now, is SO2 polar or not polar, you would say. Right. So my answer would be I can't tell you yet because that's my Lewis dot structure. What do I need to put it into? I need to put it into the Vesper geometry. So I need to put it into my Vesper geometry. So what is the geometry then around that sulfur? Okay, bent. I mean, bent is a molecular geometry, but it would be bent. It would be trigonoplanar. right? Because I've got 2 bonds and a lone pair, that's 3. So that means that it would be, let's not worry about its hybridization, but let's worry about its, well, we could, but we're not going to. So in other words, with a lone pair and with 2 bonding, there's 3, so that's going to put it into a trigonal planar geometry, including the lone pairs. Don't include the lone pairs as bent. But either way, it's not going to be linear. So the sulfur is going to have 2 down here, and then the lone pair up there. And I'll erase that. My intent was to show a bond, show sort of like the lone pair would be up here. Okay, it's bent. It's trigonal planar. Sulfur. Who's more electronegative, sulfur or oxygen? Oxygen, because going up the periodic table. So that's going to go like this. Are those canceling? No. What about the arrow for the lone pair? There isn't one. Remember, we ignore the lone pairs. So it's only the bonds.
So the overall dipole moment would be down.
The overall dipole moment would be down. And so this is where the delta minus is. This is where the delta plus is. The key thing is they don't cancel each other out. And so is SO2 polar or non-polar? It's polar. So CO2 is non-polar, but SO2 is polar. So we can't just look at, well, we can if we can picture them immediately in our minds. Maybe CO2, you could have done that from general term. But we're always better off to draw a Lewis dot structure, put it in the geometry, and go from there. So SO2 is polar, CO2 is not polar. Which is, CO2 is not polar. So just as a practical, something practical, carbon tetrachloride was non-polar as well. So the reason it's used in dry cleaning is because it's non-polar. Greases and oils, which I should say, your typical grease and oil is made up of carbons and hydrogens. And so it's also what we would consider to be non-polar because the CH bond is relatively non-polar because there's not that big of electronegativity difference. So carbon tetrachloride is able to dissolve the greases and oils, and that's why it's used in dry cleaning. But then the problem is it gets into the soil, and then when it gets into the soil, it goes down into the water table. And like in Tennessee, this is probably 20 years old, but somewhere in Tennessee, there's a huge lake of carbon tetrachloride just floating around in the soil. And when it gets to the water table, that's going to be bad. So if you want to be an environmentally green dry cleaner, the thing you should use is CO2, because CO2 is non-polar, so it could replace the carbon tetrachloride. But then you say, well, how do you clean something with a gas? And you don't. You squeeze the CO2 until it becomes a liquid, and then you take the liquid CO2 and you run it through your clothes. And then you let the CO2 escape, you collect it, because otherwise you're trading one problem for another problem with CO2 and a greenhouse gas. So then you let it escape, there's your oil and grease, and then you repressurize the CO2 into liquid and use it again. I don't know how many environmentally friendly dry cleaners there are, but that's one way to do it. I have one of those instruments in my lab that you could put, for instance, like flowers in it. You could get like the fragrance out of the flower. It's not, it doesn't make a traditional essential oil. In lab, you guys are you're gonna do steam distillation of cloves. No, yes, cloves. And so you're gonna collect clove oil. That's the way you traditionally get an essential oil. But you can use CO2 as well. but sometimes it doesn't quite smell exactly the same. I've been doing I did senior exit interviews a few weeks on seniors, and so I'm trying to include more practical stuff because apparently that helps people learn, because if they can relate that. So CCl4, CO2 are the same when it comes to polarity. But that's how we go through. So if we just looked at CO2 and we left it like this, we're going to say it's non-polar, but it is polar because I have to put it into the correct aspect. So, are we done yet? No. Because now if we determine whether the molecule is polar or not, what's the last thing we can do with that information? And the last piece of general chemistry that we need to review. So we went, again, Lewis dot structures, resonance, Vesper theory, hybridization, which go together. That gives us a three-dimensional geometry. Why do we need the three-dimensional geometry? Because we need to know whether the molecule is polar or not. Why do we know whether the molecule is polar or not? Because we need to know what kind of intermolecular forces it undergoes. Who cares about intermolecular forces? Well, there's a big difference between H2O and H2S. Or there's a big difference between CH3OH and CH3SH. Come back to that. So, intramolecular forces are our bond energies. We don't care about those right at the moment. We're not breaking bonds. We will, but we don't need that right now. Intermolecular forces between the molecules, what's that going to tell us? If those forces are weak, the molecule is probably going to exist as a gas at room temperature. If they're stronger, it's going to exist as a liquid. If it's really strong, it's probably going to exist as a solid. Why do two materials have different boiling points? Could be their intermolecular forces. Could also be that one's heavier than the other in terms of molecular weight. So the intermolecular forces are important because that's how we're going to determine whether things are solids, liquids, or gases. What temperature they're going to melt at, what temperature they're going to boil at, is all based on the intermolecular forces. So what kind of intermolecular forces do we have? We've got induced dipole, which are called London dispersion forces. I don't know if that term's currently in vogue or not. These terms come and go. I'm usually the last one to know that they changed them. So dispersion, induced dipole is fine. That's when you have two nonpolar molecules. When you have two polar molecules, you're going to have dipole-dipole. When you have an ion and a dipole, which we're not going to really talk about too much, that would be an ion dipole for ion and polar molecule. And then hydrogen bonding is the special type of dipole-dipole. And when do you have a hydrogen bond? You have a hydrogen bond when the hydrogen is attached to an O, N, or F. And I'll give you the exact example because there are times when people have issues trying to determine if something is truly a hydrogen bond or not. But hydrogen has to be attached to an O, N, F. What's special about O and F on the periodic table? Those are the three most electronegative elements on the periodic table. So hydrogen bonding is stronger than a normal dipole-dipole force because the hydrogen is attached to one of the three most electronegative elements. And so, what's induced dipole? Induced dipole, that occurs between either two atoms that are the same, like hydrogen or two chlorine atoms. Induced dipole. Induced dipole just means that if we bring two atoms or we bring two nonpolar molecules together, since there is no charge on their surface, there's no delta plus at this end and delta minus at this end, since it's all the same charge, when they come together, the best they can do is sort of distribute their electrons so that for a fleeting minute, like a fleeting fraction of a second, they're going to generate a delta positive at one end and delta minus to be able to be attracted to each other. But this is not a permanent dipole. So they'll create just a fleeting charge difference to hold them together. That means it's pretty weak. And so that's the weakest of all the forces. And that's going to occur when you have two nonpolar molecules. Again, what does that mean? That means their surface has the same charge. Now when you have a dipole force, and this doesn't print out very well, but these are CCl with three H's over here. Is CH3Cl a polar molecule? Yes, because it's tetrahedral, but it's not all the same atom. The chlorine would be the delta minus end. The hydrogens would be the delta plus end. So if you think about lining up some CH3Cl molecules together, the chlorine end of one molecule is going to be attracted to the CH3 end of the other. And that's kind of what this shows. This is stronger. Why? Because those delta plus and delta minus charges permanently exist. They're not induced by bringing two molecules together. They permanently exist. So if I go back to my alien example, the stronger the delta plus delta minus difference is, the stronger the dipole force would be. So if it's pretty wimpy delta minus delta plus charges, it's going to be weaker dipole, but that's still better than nothing, or a quickly induced one for the nonpolar molecules. Again, it's electrostatic force. If you had an ion and a nonpolar molecule, or if you had an ion and a nonpolar molecule, it's going to be pretty weak. But if you have an ion with a polar molecule, that's going to be much stronger. So if you think about having like a sodium ion in water, the sodium plus with a full-blown +1 charge, not a delta plus, but a full-blown +1, interacting with a delta minus, that's a much stronger force than delta plus, delta minus. So you take your sodium chloride, you take your salt, you dissolve in water. All of those ion dipole interactions are going to be able to overcome the ion-ion force of crystalline salt. And so the salt will dissolve in the water. And so that's what happens. If you want to know whether an ionic substance will dissolve in water or not, you got to take into account all the energies. So you got to think about, well, how much energy is it going to cost me to break these guys apart? Remember, they're in a three-dimensional lattice. They're not just in two dimensions. So pulling one sodium out means you got to get it away from 1, 2, 3, 4, 5, 6 other chlorides. But can I do that? Am I going to get enough energy out when I come over here? Yes. If I don't, I may have to have a little bit of energy put into the system. So for instance, you put sodium, when you add salt to water, does the water boil? Does the water get hot? Does the water get cold? Pretty much no change. If you take calcium chloride pellets, like we use to de-ice the driveway, throw that in water, it's going to get hot. You might even be able to put it in a styrofoam cup, add calcium chloride pellets and melt the cup. anything to do that with. But you'll generate enough heat to really get the water hot. On the other hand, if you sprain your ankle and they bring one of those cold packs over and smash it, smash the water into the salt and it gets cold, that's ammonium chloride. So in that case, it's taking energy from the surroundings, your ankle, and dissolving the system that way through energy. But in order for the endothermic reaction, you got to be pretty close in it. So you got to be pretty close if you're going to get back what it's going to cost here. But there's one more thing though that I'll talk about in a moment. There's one more energy that isn't quite there that we need to consider. Well, let's talk about hydrogen bonding. So when do you get a hydrogen bond? You get a hydrogen bond when the molecule is polar. And the molecule will automatically be polar if that hydrogen is attached to an O, an N, or an F. However, if you have an H attached to an O, N, or F and you have all the same molecule, you're going to get a hydrogen bond. The true hydrogen bond looks like this. That's the hydrogen involved in the hydrogen bond. So one of the things that sometimes people say is that really a hydrogen bond? The hydrogen in a hydrogen bond has to be covalently attached to an O, N, or F. And it has to be electrostatically attracted to an O, N, or F. So around that hydrogen bond has to be O, N, or F. It can't be, well. So this hydrogen has to, this is the covalent bond. So it has to be covalently bonded to an O, N, or F. And then it has to be electrostatically attracted to another O, N, or F. And if you're only talking about a single molecule, like if I was to say, and I've got a cuter picture of this, but if we were to look at the hydrogen bonding scheme in water, since water is all the same molecule, the hydrogen has no choice but to be covalently bonded to an oxygen and electrostatically bonded to another oxygen. If I have two molecules, that may or may not be the case. But the hydrogen bond, this is the hydrogen bond right here. So for instance, if I took a methanol molecule, this is a 1-carbon alcohol. We'll learn about functional groups. The OH is an alcohol functional group when it's attached to carbon. Methanol is not what you drink unless you want to go blind and die. 2 carbons, ethanol, depending on your age, it might be legal or illegal for you to drink that. Big difference between 1 carbon and 2 carbons. But the OH there cannot, this hydrogen would not form a hydrogen bond to the carbon. So that is not a hydrogen bond because the hydrogen cannot be electrostatically attracted to carbon. So the hydrogen bond would be H in between 2 O's, in between 2 N's, in between 2 F's, in between an O and an F, etc. So it's covalently attached to one, but hydrogen bonded electrostatically. Why is that so special? Maximum delta plus on the hydrogen, maximum delta minus on the other atom, maximum delta H attracted to the maximum delta minus gives me the maximum dipole-dipole interaction. And so hydrogen bond is in a class by itself. And it's not just uno hydrogen bond that makes the system more stable or makes water what it is. It's the fact that there's tons of hydrogen bonds in the molecule, and you add those small forces up over billions of molecules and you've got something significant. Here's an example. If I was to go get a bottle of methanol or ethanol, pure ethanol, and I was to take the cap off of it, you're not going to smell it for quite a while, because it has a hydrogen bond, so it's going to have a very high boiling point, relatively speaking. Now, water boils at 100 degrees Celsius. Methanol probably boils at like, I don't know, 78 or so. The addition of the carbon with that non-polar end is going to reduce the boiling point, but still it's got hydrogen bonds. So that's not going to be too bad. I bring in a friendly skunk. And I anger it, which it doesn't take much to do. Probably scare it more than anger it. And I don't know, apparently cats and skunks have this mutual agreement where they don't like spray each other. But I bring a skunk in, I put it on the table, aggravate it, you're gonna know. Because the skunk is locked and loaded with what's called methane thiol. Once it sprays its methane thiol, that does not have a hydrogen bond because sulfur is not one of those three atoms. And so that SH is just going to be a dipole-dipole force, not hydrogen bonding. So methane thiol is a gas. Methanol is a liquid at room temperature. So if somebody hits, well, if a skunk accidentally gets in front of a car, I mean, you're going to know about it for blocks. Right? And methane thiol is what they put in the actual gas. Because methane has no smell. A little bit of methane thiol goes a long way. So they tell you if you smell rotten eggs, that means you have a gas leak. It's the methane thiol that's in the gas line. But why is it a gas? Because it doesn't have hydrogen bonding. Sulfur is not oxygen. Even though they're right below each other, they have different physical properties. So no hydrogen bonding, just dipole bonding. So when it comes to intermolecular forces, then the hydrogen bonding, it's basically two nonpolar molecules, induced dipole, or just nonpolar, polar, induced dipole, dipole. Two polar molecules without the OH, NH, HF, that's going to be dipole-dipole. Have the OH, NH, HF, it will be dipole-dipole. So that's where you get things like this. You know, this is your water. You got hydrogen bonds when it's liquid or solid. That's a cuter picture of it. Use that for the non-science majors class. It doesn't exist anymore. When it freezes, it expands. Why? Because those hydrogen bonding networks then form hexagons that cause the water to expand. And if your object is completely full of water, it's probably going to break because that's a pretty strong force. hence the potholes. Water gets down into the asphalt, freezes at night, starts breaking it apart. If you live in this climate, you get lots of potholes. It's mostly because of the freeze-thaw cycle. And so then you end up with a tetrahedron. Also with hydrogen bonding, you can end up with hydrogen bonding in biomolecules or in things like in amide. We'll talk about this functional group. This is C double bond O with an amide. So when you're forming a protein, you're going to take the NH and hydrogen bond it to a C double bond O. So here's a perfect example of what I was talking about. This is what? Beta sheet. Something like that. I'm assuming there's more biology majors in here. That'll be something there. So that's like what? Beta sheet, parallel sheet, anti-parallel sheet, something like that. This hydrogen is attached to a nitrogen on one side and an oxygen on the other. That's the hydrogen bond. It's the lithium hydrogen bond. Could I form this hydrogen? Could I form a hydrogen bond to that carbon? Nope, this carbon's not nitrogen. Not nitrogen. So these hydrogen bonds are strong enough to form beta sheets, to form your alpha helixes. So these are proteins, protein alpha helixes. They're strong enough in here to form your base pairs of your DNA, and hold the DNA together. But again, it's got to be a hydrogen in between a nitrogen, oxygen, fluorine on this side, nitrogen, oxygen, fluorine on the other side. In the DNA structure, there's some places where, for instance, there might be a hydrogen off here, but if there's a carbon there, it's not. So, strength. Ion dipole strongest, yeah, we're not going to deal with this. Hydrogen bond, strongest. Dipole, next strongest. Dispersion, weakest. If you're into flowcharts, there's a flowchart. I'm usually into flowcharts when you develop your own flowchart, because in doing that, you're learning. I think I said yesterday, well, let's see, had my semi-inspirational talk to new incoming freshmen yesterday. It's like, do you have good study skills? Do you even know what study skills are at this point? Because I'd just be, if you ask me if I had good time management skills, all I can tell you is no, because I don't. But if I did, what characterizes that? Anything you do, if you're recopying your notes, when you're reading the book and taking notes, remember, you're learning. Hopefully. When you're doing problems, you're learning and practicing. I don't know if they got that yesterday. If they did, they're gonna have if they didn't, they're gonna have probably an interesting ride back home with their parents. If the parents got it. So, if you're into flowcharts, this is great. If you develop your own flowchart, that's better. My job is to kind of give you multiple ways to look at it. Whatever works for you is great, because the one thing I do not do is I do not mess with student systems. If you have a system, I'm not going to mess with it. I have research students that would tell me, don't mess, I got the system, don't mess with it. And I will not mess with your system, whatever it is. Here's the last thing, as far as intermolecular forces. Because, how do you know if two things are going to be soluble? What's the phrase? Light dissolves light. Like what? What's the light? So we're talking about the polarity of the molecules. What are we really talking about? The intermolecular forces that they undergo. Because if I want to know if the light is going to dissolve the other light, it's all about energy. I got to break apart two pure substances. The solvent and the solute. I got to break the solvent apart, I got to break the solute apart, and then when I bring them back together, I hope I get enough energy to pay for what I just did in breaking those two apart. If I'm close, then it's an endothermic reaction. Swallow heat, get it to the cell. If I'm over, then it's exothermic and I get energy out. If it's too far, if I don't get enough here to do those first two steps, it ain't dissolved. So it's all about the energies required to break things apart. My absolute, I guess, last thing. Why doesn't a wax or a non-polar substance dissolve in water? It's this slide. Why does oil and water not mix? Can I break apart the non-polar solvent? Does it take a lot of energy to do that? To break apart a non-polar solvent? Does it take a lot of energy or a little bit of energy? A non-polar solvent, or a non-polar substance. Does it take a lot of energy to break those induced dipole bonds? Or the molecular? No. It doesn't take much energy to break apart my non-polar solvent or my non-polar substance, because it's the weakest intermolecular force. Now, am I going to get a lot of energy out when the water interacts with the non-polar substance? No, I'm not going to get much energy out. But what's the killer of this process? Where does it take a ton of energy? It takes a ton of energy to break the water molecules. So this is easy, but this is not. So I don't get nearly enough energy out of that interaction to pay for breaking the water apart. That's why oil and water doesn't mix, because I can't break apart the water molecules. I don't get enough energy. Now, that's kind of a general chemistry thing. If we can use that in organic, we will. But just remember that the fundamentals here are, I got to break those two things apart, bring them back together. And if one, it's going to cost too much energy and I'm not getting it back, I might get enough energy back from the non-polar polar. But I'm not going to get enough to break the polar polar apart. So that's our intermolecular forces. Right. For tomorrow, day 3. We can count days. So for day 3, the reading this is our first truly organic topic. Yay. It's going to be 2.0 to 2.5, and then the beginning of chapter 5. This textbook does something that I tried in the fall of last year and failed probably miserably. It tries to talk about the naming of all molecules together, and that's too much. It also tries to foreshadow things that no one remembers when we get to them. So that's why I'm skipping chapters 3 and 4 right now. And I talked to other people last week and I said, what do you do with those chapters? And they said, ignore them. They said, I just use my own system. So that's why it jumps from 2 to 5. Okay? There's a lot of stuff in there. So if something doesn't make sense, I'm gonna probably spend a lot of time lecturing, but I don't have to if you don't have questions.
Are we doing all of that?
I think it's up to 5.8.
Okay.
It's on the sheet on the reading list that's on the syllabus. Plus, it will also be within an hour or two in tomorrow's folder. I'm not ahead yet, so that's the first thing I'll do is put that online. So again, after you can do some of those problems, if those we're still kind of in a catch-up mode. So if you want to come to class tomorrow and then go back and answer the problems, that's okay as well for the moment. I'm violating a lot of rules here because I should give you very specific, clear-cut instructions with no wavering, and I'm wavering. But there's quite a bit of stuff for tomorrow, so we will go over that. But if you could go through and read through it and see what makes sense and what doesn't make sense. If you're like, I didn't know what to, fine. I mean, that's what I will lecture on. If you don't want to try the problems and want to hold off, that's fine. Like, go back, do the hybridization problems. Will probably be easier to do now from yesterday's reading. So that's what we're going to do. We're going to talk about alkanes and cyclic alkanes and conformational analysis. It's a lot of stuff in one day, but that's what we're going to talk about tomorrow. I will release some practice problems, some written practice problems for polarity and intermolecular forces, and I'll find the hybridization, sketching those out, and I will put those in the folder if you want to try some of those. On the older exams, you'll see I usually ask some of those questions. So there's also older exams you can use those practice problems as well. But I'll put all that and I'll send you an email when everything's ready. If you have any questions, shoot me an email. I don't think I set up the discussion board yet, but I'll try and do that. Or stop by. My office is the big office at the end of the hall, down near the elevator. The door's open. I don't have an admin for the summer, so you just have to come in and, I guess there's a bell you can ring, but if you just come in and yell, I'm in the back left. So that's where you can find me. But if not, shoot me an email. I'll be on email. Okay. All right, I will see you tomorrow then.